Hello everyone, how are you doing? All are doing good? All are staying healthy and fit? That's good. I'm Mahesh, your physics teacher, and you're watching SMR Online Physics. Now coming back to the intro video, what you just saw before me on the film, what was that? What was that exactly? I mean to say, why did the letters kept on becoming magnified as the water kept pouring in the vessel? Is there any answer for it? Yes, definitely the water was acting as a magnifier. And this phenomena, my dear, you got it right. This is called refraction of light, and that is the topic for today's class. We are going to discuss refraction of light in the best visual way possible. So here we go. Refraction of light. And you are not late. This is the first class on the topic of refraction of light. Hope we continue throughout the series. See you, right? So let's get ready to learn in the best visual way possible, refraction of light. As you see here, when someone sees into clean water, not only the bottom of the container is visible, but one can see their own image in it, as if the surface of water is behaving like a mirror. How and why it happens? It happens because when a ray of light propagates from one transparent medium, air in this case, into another transparent medium such as water, as you see here, it does not go straight as it should have, but rather it changes its direction of propagation. In doing so, some bit of light also gets reflected off the interface, because of which one can see their own image in the surface of water. But most of the light actually transmits through reflecting very little bit of light. This is what exactly happens. This change in the direction of propagation of light is called as refraction of light. Also, you might have noticed that as this water, or to say the bottom of the surface of the container or the vessel in which the water was kept, also is an opaque medium. It's an opaque medium. So the opaque surface, the bottom surface, bounces the light off, just plain reflection takes place. But now water has to go from water, that is one medium, to another medium. That is now going from water back to air. As it goes back from water to air, it transmits in a very bent direction. And finally, these light rays fall into the observer's eyes, which also makes to see the observer the bottom of the vessel. But very interestingly, the bottom of the vessel looks upraised. And this is all because of refraction of light. Such kind of examples, plentiful, exist in our day-to-day life, such as we are going to see right now. Here you see a straight rod, when dipped in water, looks bent or broken at the air-water interface. Also you see the mug dipped in water looks shorter in its length. Here again you see the coin, as it gets immersed in water, looks magnified and slightly upraised. And the lemon and fingers also look magnified than their actual size. The effects of refraction gets exaggerated when light tends to propagate obliquely rather than traveling straight. So now let us learn why this all happens. Why exactly the light gets refracted. Alright? So let us look into that with the help of some very simple ray diagrams. Alright? So let me draw a very simple ray diagram. First of all, I show you the straight line. This straight line will indicate the separating layer between two different transparent mediums. So one of the most common transparent mediums is air, and in my example or the visuals, I was commonly preferring water as the other transparent medium. So let us continue with the same two transparent mediums. So what exactly happens? This separating layer, let me just name it over here. This is called interface. Interface, or simply the meaning is the separating layer between two different transparent mediums. So a ray of light coming obliquely from one transparent medium trying to pass through or transmit through another transparent medium that is wanting to go in the original direction doesn't do so. And let me tell you why. This dotted line which I am drawing right now, passing through the point of incidence and making an angle of 90 degrees with the interface, is definitely well known to all of us. It is called as the normal, an imaginary line. So what exactly happens is that in this case, as light travels from air into water medium, rather than going straight, the ray of light actually bends and goes something like this. So if you observe this diagram closely, it looks like the original direction and the actual direction of the refracted ray is actually bending towards the normal. This bent of light, or this change in the direction of propagation of light, is what we call as refraction of light. Okay? Now, let me name the ray diagram. Let me call it as P striking at O and going towards R. So definitely, it's very clear, the ray of light PO, I label it here, it is called as the incident ray of light. The point O is called as the point of incidence, and the ray of light OR, let me name it here, this is called as the refracted ray of light. Okay? This happens when ray of light or a beam of light happens to propagate through two different transparent mediums. Alright? Now there's an angle created, as you can easily see that. The angle between the incident ray and the normal. This angle is very appropriately labeled as angle I. What is angle I? Yes, definitely know that. Angle of incidence. Let me just label it over here. This is called angle of incidence. Similarly, the angle between the normal and the refracted ray, this tiny angle, is correctly labeled as angle R, but not to fall in the trap, the name is now something new. This is called as angle of, yes, it is angle of refraction. Alphabet is same, just like your angle of reflection, but here it is called angle of refraction. Let me tell you something more. In this case, the original direction which is shown by the dotted line and the actual direction shown by the pink line, there is an angle of deviation created. This is the angle by which the ray of light did not go straight, but rather it has bent inwards towards the normal. This is called angle of deviation. So let me write it over here. This is called angle of deviation. So if you observe this diagram very closely, we find from the point of view of angles also that angle I is definitely greater than angle R. This is a very important point to be noted. And it happens when it has traveled from air into water medium. But at the same time, I can also see that from geometry of vertically opposite angles, angle I is equal to angle R plus angle delta. That is the angle of deviation. So from this, we can also find out angle of deviation should be equal to angle of I minus angle of R. That's it. This is one case by which a light ray can get refracted. Please note it down. Now let me show you what would have happened if the ray of light would have propagated from water into air medium. Okay, so let us see very quickly this line. Now you know it better. Let me call it by the same name, the top medium as air and the bottom medium as the water medium. All right, so this line is generally known by the name interface, or in simplicity, the separating layer between the two different transparent mediums. Now a ray of light passing obliquely from the water medium and trying to get into the air medium, actually the original direction should have been something like this. It should have obeyed and followed a straight path. Yeah, it looks straight. So to get your reference right, always without a fail, draw your normal. Let us call it as N dash, the normal. Now you see what's going to happen. In the previous diagram I showed you what has happened for the ray of light coming from air into the water medium. Now the ray of light is propagating from water into air medium. Now in this case, my dear students, the ray of light definitely changes its direction of propagation, and rather it goes in such a fashion. So if you observe very closely the ray diagram, you will find as if the ray of light has refracted away from the normal. Is that clear? It clearly looks bending away from the normal. So let me give you the names once again. PQ, what should be PQ called as? Right, this is our incident ray of light. Similarly, Q goes it towards the R direction. So QR has its own name. This is called as the refracted ray of light. Is that clear? Q will be termed as the point of incidence. So get this terminology very, very clear, my dear students. And now, as I already told you, N dash will stand for the normal. Normal always passes through the point of incidence and makes an angle of 90 degrees with the interface. Is that clear? Now, looking into the angles part, in this case you find the angle created between the incident ray and the normal is this. So this angle should be called as angle I, that is named as angle of incidence. And similarly, the angle between the normal and the refracted ray, this angle is denoted by angle of R, and angle of R is called as angle of refraction. Is that clear? Now one important angle is there, which I discussed in the previous case also, that is the angle of deviation. So you may even try to find out which should be called as the angle of deviation. Definitely this is the original direction shown by the white dotted line, but this is the actual direction of the refracted ray. So the light ray has bent by this angle away from the original direction. So this is your angle delta, which is called as angle of deviation. Very, very important. So what is the major difference you find in this style of propagation when a ray of light goes from water into air medium is that the measure of angle I is now relatively smaller than angle of refraction. By the measure, angle I is greater than angle of I. At the same time, looking into the vertically opposite angles geometry, we find that angle I should be equal to, what do you say? Angle R minus the angle of delta. If you just subtract this out, you'll be getting this equals to this. That's it. So from here, angle of deviation will be equal to angle of refraction minus the angle of incidence. That's your second case of refraction. My dear students, a light can be refracting in two possible ways. This is the case 2 and the previous is the case 1. Either it can bend towards the normal or it can bend away from the normal. So let us quickly get into the cause for refraction, which is the ultimate question. Why exactly a light ray changes its direction of propagation as it travels from one transparent medium into another transparent medium. In the meanwhile, please note it down. Okay, now let me show you what would have happened if the ray of light, rather being incident obliquely, it just strikes along the normal. What would have happened in such a case? I already showed you a visual, a practical visual. Even if it was the same air and water medium, and the ray of light, or if you shine a beam of light along the direction of the normal, that is incident perpendicularly on the interface at an angle of 90 degrees, the ray of light would not have bent or changed in its direction, rather it would have gone along the same straight path. So exaggerated refraction will be the minimum most when you see or when a ray of light propagates perpendicular to the interface separating the two transparent mediums. All right, so it would have gone exactly straight through it. All right, so now after seeing through all the possible three cases how a light can get refracted, let us come back to the most important question of this class. Why exactly light got refracted? In simple language, I mean to ask, why did the light change its direction of propagation as it traveled from one transparent medium into another transparent medium? Okay, let us quickly learn the reason. So this is the important part of today's class, the cause for refraction of light, which actually created all the beautiful illusions which I have shown you in the first part of this video. All right, cause for refraction. Why exactly the light got refracted? The reason is simple, my dear students. The reason is simple. Here what happened is that when a ray of light, or you say a beam of light, goes from or travels from one transparent medium into another transparent medium, it is best understood when we consider light as a wave rather as a stream of particles. A wave will have its characteristic properties like wavelength and frequency. So it is said that, it is believed and it is practically and experimentally confirmed that when a ray of light or a beam of light propagates from one medium to another, its speed actually changes in the medium. So I mean to say, the real cause of refraction is the change in the velocity of light. And you know very well what do you mean by velocity. It is the magnitude, that is called the speed, plus the direction. So here you can see that the ray of light is coming in a specific direction, and now after striking at the interface, everything happens at the interface, please mind it, my dear students. After striking it over there, now the light ray goes slightly in a different direction. It means to say the direction of propagation has changed, and what has changed in the visuals, if you can focus properly, is the wavelength of the light wave has actually decreased. Alright, so rather than going in the original straight path, in this case the light has actually bent inwards, and the reason is the change in velocity of light. That means the speed as well as the direction of light changes. So in this case, the speed of light, you should know it, is given as a product of its wavelength and its frequency. So what I said here, please note it very carefully. I said when it goes from one transparent medium into another transparent medium, the wavelength changes. I mean to say, this factor changes, not the frequency. Frequency is the character given to the radiation by the source of production itself. The source of light decides what should be the frequency of the radiation, but the wavelength can change as it changes the mediums, as the light travels through different mediums. So when wavelength changes in a medium, definitely the product of wavelength and frequency also will change, and the product of wavelength and frequency is exactly equal to the speed of light. So if wavelength changes, the speed of light also will change. That is what exactly is happening. So this changes in the velocity of light, this change in the speed and direction of the light as it propagates from one medium to another, is given a very new scientific terminology. It is called optical densities of the medium. It is called as the optical densities of the medium. Optical densities are slightly different, in fact exactly very much different from the mass density. I mean to say, mass density is mass per unit volume, but optical density refers to the changes in the speed of light as light propagates through various mediums. Because, my dear students, as light is a radiation and as it propagates through one medium, it continues to travel straight through that medium. But as it strikes at the interface, some bit of its energy is getting absorbed, and some getting slightly reflected off, as I showed you in the first part of this video, and major amount of energy is getting transmitted through. So there is absorbance as well as transmittance. So it depends upon how much is getting absorbed and how much is getting transmitted. So that is measured in terms of optical densities of the medium, which gives us a measure of the speeds of light in various transparent medium. Greater the absorbance and lesser the transmittance, I mean to say, the velocity of light would be lesser. Or greater is the transmittance and lesser is the absorbance, that it means the velocity of light would be much more higher than the other medium in consideration. Are you getting my point clear? Is that clear? Am I clear to you? Okay, right. So optical densities can be classified into like two kinds. Certain mediums can be called as optically denser mediums, and certain mediums can be called as optically rarer mediums. All right? So let me just make it clear, it's different from mass density, as I told you. For example, the classic example is between kerosene oil and water. Kerosene oil, everyone should have seen it in real life, it's blue colored liquid, is actually lighter than water. It means less in terms of mass density. That's why you'll find kerosene floats on water. All right? But in terms of optical density, kerosene will be termed more optically denser than water. It means light tends to travel more slower in kerosene than in water. So optical density has something to do when light interacts with the various particles of matter, like the atoms and the electrons and the ions of a given medium. And that decides what should be the optical density of a given transparent medium. Alright? So let me rub this off and let me just make it very easy and clear to you. Optically denser. If a medium has to be called optically denser, it means the light travels relatively slower in that medium. If the medium is called optically rarer, then it means light travels relatively faster. Hope I'm very clear to all of you. Optically denser, optically rarer. It means in this case, if the ray of light is coming from air and getting into water medium, so in one of the mediums the light should have been traveling faster, in the other medium the light should have been traveling relatively slower. Okay, that is what I mean to say. So from practical experimentation, it has been found that as light propagates from air into water, the speed of light decreases in water medium in comparison to the speed of light in air medium. So, according to this new terminology, water should be called as optically denser relative to air, or you could have said air should be termed optically rarer when relative to water. I get a point here? Is that clear to all of you? Yes. From this, we can come to a very good conclusion, and I can make it much more easier to understand. So if I say the ray of light is propagating from optically rarer to optically denser medium, if you have understood, I hope so. If you have understood the concept of optical density, it would be very easy to draw. Optically rarer to optically denser means the light speed in the denser medium is going to decrease relatively, hence it will be shown as if it is bending towards the normal. This would be the reference direction, bending towards the normal. So I mean to say, if the speed of light in the first medium would have been v1 meters per second, and the speed of light in the second medium changes to some other number called v2 meters per second, it would be very easy for you to easily classify that v1 has to be numerically greater than v2. This is the way to be understood the change in the speed of light. On the other hand, if the ray of light happens to travel from optically denser mediums to optically rarer mediums, then you would have easily shown it by something like this. Rather than going straighter, denser to rarer. So as it goes from denser to rarer, the speed of light is going to increase relatively to the speed of light in denser medium. Please remember, it's all because the wavelength of the light radiation changes as it passes through various mediums, not the frequency. Please keep it in your head. So here it will bend away from the normal. That's it. So here, if the light speed would have been v1 meters per second in denser medium, and it goes with some other number like v2 meters per second in the rare medium, where you can easily see it seems to bend away from the normal, then numerically you would have easily said that v1 in fact is lesser than v2 meters per second. My dear students, this is it. This is why you saw plenty of illusions in the initial part of this class, as I showed you plenty of visuals, which we get to see in our day-to-day life. That's it, either bending towards the normal or either bending away from the normal. So hence we can conclude from today's class what we have learned. that as light propagates from one transparent medium into another transparent medium, the speed of light changes due to the change in optical densities of the medium, which in turn changes the direction of propagation of light. Hence, light refracts and thus gives us beautiful illusions which we get to see in our day-to-day life. Can we measure the optical densities of various mediums? I mean to say, will light bend the same in kerosene oil, alcohol, and water? Three liquids. Will it bend by same angles in all the three mediums? Because they are all in the liquid state of matter. Think about it. We'll get to the answer in our next class. So stay happy, stay fit, and stay tuned to SMR Online Physics. See you again, because physics is all about fun. Thank you. Have a great time. Bye.